Alright, in this video we're going to revisit the three problems that we set up in part 1 for our related rates problems. And so in this section, this part, what we're going to do is use those relationships and diagrams that we already came up with to solve and answer the problem that's being asked. Alright, so in number 1 here, we had a ladder 25 feet long, leaning against a house. We're told that the base of the ladder is moving away from the house at a rate of 2 feet per second. We want to know how fast the ladder's top is moving down the wall when the base of the ladder is 7 feet from the house. So just to recap what we had, right, we have our ladder there leaning against the wall. We defined these two variables, x and y, x being the distance that the base of the ladder is from the wall, y being the physical distance from the ground up to the top of the ladder, wherever the ladder is touching the wall. And so we got, because it was a right triangle, we were able to come up with, or just really use the Pythagorean theorem to say x squared plus y squared is equal to 25. Okay, so in this video to actually solve them, we're going to go through pretty much a three-step process where we want to identify what's given to us. So we've already got our diagram, we've got our relationship between them, but we didn't ever talk about the rates that were given to us in the last video. And so for this, we're given that the base of the ladder is moving away from the house at a rate of 2 feet per second. And so what's given to us is the change in x over our time is going to be 2 feet per second. And so we want to make sure that we're identifying that so that we can use it later. And then we want to figure out, well, what is the question asking us to do? And that is looking at the question itself, which is how fast the ladder's top is moving down when the base of the ladder is 7 feet from the house. And so typically the question is going to be a two-part thing. It's going to ask you about to solve one of the rates, but it's also going to do that when one of the variables is equal to a given number. And so our question here is asking us to find dy dt when x is equal to 7 feet. Okay, and since our dx dt was a positive 2, which we were able to leave as positive because we were going away, right? So in the last video, I think we labeled this with a little arrow going there to the right. The right is a positive direction, so we're going to leave that as a positive 2. Now that we have our given information identified, we know what we're trying to get, the rate that our ladder is falling when the base is 7 feet away. We need to solve it, okay? And in order to solve for that, we need to take that relationship, and what we're going to do is we're going to differentiate it with respect to time, right? Neither of those variables are, nowhere in there do we see rates. We know that we're given a dx dt, but that's not in our relationship. We're trying to solve for dy dt, also not in our relationship. But what we can do is differentiate this with respect to time. And this is going to work very similar to implicit differentiation, where as we take the derivative, we're going to add in these, because the variable that we're differentiating in respect to is not in the problem yet. We're going to add in those. And so we can use the power rule for x and y here to just bring down the 2, right? So exponent comes down, subtract 1, so we get 2x. But unlike implicit differentiation, where we only added in the dy dx's, here we're going to add in these rates or these changes for both. And so what ends up happening is we get a 2x times dx dt, and then we get 2y times dy dt. And then same as normal, any constant is just going to be 0. So we're differentiating with respect to t for both variables. And now we can see that all of our rates that we needed show up. And so when we look at this, what we're trying to solve for in this case is this rate here, this dy dt. And so we have dx dt that we need to fill in. That was given to us. We are going to need an x and a y. And so what we're told down here in the problem is that, well, x is 7. The thing that we don't have right now is y. But we do have a right triangle, and we can use our original relationship to solve for that. And so what we do know is that our x is 7, so 7 squared plus y squared is equal to 25 squared. Hopefully you recognize that 7 and 25 are a part of a Pythagorean triple, where y is just going to be 24. If you don't recognize that, you would need to solve that for y, taking the square roots and subtracting, taking and then getting everything on one side. But this is a Pythagorean triple, so we got really lucky here, and we just know that y is 24. And so now we can take all of that information and plug it in. So we're going to say 2 times the 7 that's given to us in the problem. Our dx dt is 2. And then we're going to add to that 2 times 24, the y value we just solved for. And then dy dt is equal to 0. And so we can simplify this, and we can solve for dy dt, and we get that dy dt is equal to negative 28 over 48. And we can simplify that. We cannot simplify it, not really an issue. And then we want to make sure that we get units on there as well. So your change in y, the rate at which the top of the ladder is moving down, is negative 28 over 48 feet per second. Now, something that you want to make sure you're okay with is the negative, right? So when we see that your rate is negative, is this okay, right? So what we're going to ask is negative okay. And in this case, yes, because the ladder is moving vertically down. So if we're moving either down or to the left, both of those are going to imply negative, because essentially what we've done in the problem is we've defined this point here to be our 0, 0. So if we were to lay this problem inside of a coordinate plane, that would be the origin, the intersection there between the ground and the base of the wall. And so, yes, we're okay with it being negative. And then we want to make sure that we're writing a sentence. You can see the answer box there says the top of the ladder is moving down the wall at 28 over 48 feet per second when the base of the ladder is 7 feet from the house. And now we get away with not having that negative because we've said that it's moving down. Okay, so when you interpret that problem, you would any negative signs would be interpreted into the direction. Okay, so that was the first one. Second one was a little bit different in the sense that now we have water that's running into a cone-like tank at a rate of 9 feet cubed per minute. In the last video, we also talked about how this was a volume. All right, because of the units, we can interpret that as the volume. We're told that the tank stands point down, so we drew almost like an ice cream cone that's being filled up with water. We were given a bunch of information that the height was 10 feet, base radius was 5 feet. This allowed us to come up with the relationship between those using similar triangles, so we get our volume in terms of just the height here. And we wanted to do that because of what the question is asking us, right? So when we go over here and we look at what the question is, right, we're saying how fast is the water level rising when the water is 6 feet deep. So nowhere in there are we talking about a rate that the radius is changing or when the radius is a certain amount. Okay. And so we want to go through our given information. So we're told that the volume is changing at a rate of 9 feet cubed per minute. Okay, we can leave that as positive because our water is running into the tank. So if your water is going into the tank, it's a positive rate of the volume changing. If the water is leaving the tank, then it needs to be negative. And then what we want to find is the change in height when the height is 6 feet. And so what we can do is we're going to start by taking our relationship from the last video and differentiating that with respect to time. So we get a dv dt equaling power rule here again. Don't get tripped up by the pi. Pi can just is just part of the number. It's kind of a constant out front. It's just kind of really along for the ride. So we're looking at the power rule here, bring the 3 down, so that turns our 1/12 into a 4th pi, and then reduce the exponent by 1, but don't forget to pick up that dh dt at the end, because unlike implicit, again, we need to differentiate both variables with respect to time. And then from here, we already have everything, right? We have our dv dt. We're asked about the height being 6, and those are the only 2 variables left outside of the rate, which is what we're trying to solve for. So we can go ahead and plug in and say that 9 is equal to a 4th pi times 6 squared dh dt, and we can solve for that, right? So from here, it's all algebra, and we get that the dh dt, the rate at which our water depth is changing, is equal to 1/pi feet per minute. And so we interpret that as the water level is rising because our rate was positive at a rate of 1/pi feet per minute when the water is 6 feet deep. And that brings us to the third one that we looked at, another common situation that we might run into with these problems. We have a man 6 feet tall walking at a rate of 5 feet per second towards the street light that is 16 feet above the ground. At what rate is the length of his shadow changing when he is 10 feet from the base of the light? Okay. Now in this one, the given rate, right, so right, we're going to look at what was given was the rate that he is walking towards this, and so what's changing is your dx, or your x variable. So what we can interpret this as is dx dt is equal to 5 feet per second. Except when we think about this, right, going back to that notation of if we were to overlay the problem into a coordinate plane, we're going left. Our person is walking to the left, so we need to pick up a negative here for our rate. And then what we're trying to find is a dz dt when we are 10 feet from the base of the light pole. And so 10 feet, so our x is going to be 10 there. And so now we're ready to get going on the solving. So we're going to take and differentiate this, our relationship, which we found using similar triangles, with respect to time. And so simple power rule here says 10 dz dt equals 6 dx dt. And so then we can plug in, and what we find is that there's nowhere to really plug this 10 in, and so that's not going to have an impact on what this is going to, what we can interpret this as is we're moving at a constant rate. Our shadow is not really dependent on how far we are away from the base of the lamp. And so we get, solving for dz dt by itself, this is going to be 6/10, and then we have to plug in the -5 for our dx dt, and we end up with a dz dt of -3 feet per second. And we can interpret that, right? Once again, we're going to get rid of that negative here in our interpretation by saying the length of the shadow is decreasing at a rate of 3 feet per second when the man is 10 feet from the base of the light.